All right, so 5D, they're asking us to determine the derivative of this function. So we've got x cubed times 3x plus 7 squared. So we have y equals x cubed times 3x plus 7. And then here they want us to find that at x equals -2. Okay, so obviously the first thing we have to do is just find the derivative. Now, I hope you remembered what I told you, that when you've got powers with especially product rule and quotient rule, you should be thinking about that trick we saw today to do some factoring before you do some simplifying. All right, so here, let's apply the product rule. So again, please keep track of my algebra and make sure if there's a mistake, just stop me right away. All right, so derivative of the first is 3x squared times the second function, so 3x plus 7 squared, and then plus the first function, x cubed, okay, times the derivative of what's the second function, and here I'm going to have to use a chain rule. So I think, what's the derivative of u squared? It's 2u, so times 2 times 3x plus 7, which is my u. Now that I've taken the derivative of the outside function, I can take the derivative of the inside function, which of course is just 3. All right, so since I'm actually just looking for the derivative at x equals -2, I actually don't necessarily need to simplify. I could just stick in x equals -2 here, although that would be, a lot of stuff to do. But I think it is worth simplifying. It's good practice. And what I notice here is a bunch of common factors. So I see a common factor of 3. So when I talk about common factors, this is my first term, all these multiplications. This is my second term, all these multiplications, and I see a common factor of 3. Okay, I see they both have 2 factors of x squared, so I can remove that. And I see that they both have a factor of 3x plus 7. Okay, and so now when I take a look at what's left when I factor all this out, well, it's going to look a lot better at this point, because here I've got rid of the 3, I got rid of the x squared. The only thing that's left is the 1 factor of 3x plus 7. Okay, and here plus, well, I've got rid of the 3. I still have the factor of 2. I'll put that first. I still have 2 factors. Sorry, I got rid of 2 factors of x, so I'm left with 1. Okay. And the factor of 3x plus 7 is gone. And lo and behold, I actually have something that's pretty simple now. Okay. I didn't have to work with such a long expression. So in the end, when we clean this up, we have 3x squared times 3x plus 7. And then here we're left with, so 3 plus 2, so 5x plus 7. Okay. And so now finding even the derivative at -2 is much easier. So y prime at -2. Now I can actually determine that 3 times -2 squared times 3 times -2 plus 7 times 5 times -2 plus 7. And so what do we have here? If we didn't make any mistakes, we've got, so 3 times 4, we've got 12 times, so this is -6 plus 7 is 1. And then here we have -10 plus 7 is -3. So it looks like the answer is -36. All right. So in the end, applying the product rule, and in applying the product rule, I also needed to apply the chain rule in that second derivative. Number 2 was to see so many common factors that I could remove to leave me something much simpler to simplify with. Okay, so any questions on this one here? Okay. Now I'm going to leave E for you folks to work on, because E is going to be very, very similar. Okay, because you're going to use the product rule again. You're going to have to use the chain rule in this case here, where you're doing the each of the individual derivatives, and you're going to have a lot of common factors that you're going to be able to factor out to make the simplifying much easier. Okay, so if somebody needs me to do that another time, I'll do that now, but let me save one that's a little similar. Okay. All right, so let's move on to, so we'll go in order here. We'll go to page 98, number 9. So let's see what's on page 98, number 9. Okay, so 98, number 9. So I'm pretty sure I just did one of those. Was it A or B for the person who asked that? I don't know if I gave both. If I did, just pick one.
A, please.
A. Okay, so it says find the points at which the tangent to the curve is horizontal. So first of all, I'm going to be working with a specific, I'm just going to clean that up a bit. I'm going to be working with a specific function. So presumably I want to, solve using equations. So how do we translate a tangent which is horizontal into something I can work with algebraically? So how do I interpret what a horizontal tangent is going to be? Any ideas? What is special about a tangent that's horizontal?
The slope is 0.
Yeah, exactly. So what I'm looking for is I'm looking for tangent lines whose slope is equal to 0. But of course, the way in which I find the slopes of tangents now is to find the derivative. Okay, so I'm going to take my function here. So 9a, my function is 2x squared over x minus 4. Okay, and I'm going to find the derivative of this function, and I need that derivative to be equal to 0. Okay, so I want to find the x values. Now in this case here, it says find the points. So I'm going to first find the x values, and then finding the y values is going to be easy because I can just stick it into my function to get the full coordinate. Okay, so let's start by taking this derivative here. So clearly I'm going to have to use the quotient rule. So derivative of the numerator is going to be 4x times the denominator function, x minus 4. Okay, minus the numerator function, 2x squared, and then here times the derivative of the denominator, which is just 1, all over the denominator squared. Okay, and what I want is I want this derivative to be equal to 0 since I'm looking for horizontal tangents. All right, so let's clean this up. So here we've got, what do we have? We have 4x squared minus 16x, and then minus 2x squared. All right, and all over x minus 4 squared. Okay, now notice that I'm solving a rational equation. And usually what I want to do with a rational equation is I'd like to get rid of this denominator. And since it's an equation, I don't have to worry about the whole issue with negatives with like we do with inequalities. I'm just going to multiply both sides by x minus 4 squared. Okay, so I just end up with 0 equals, and what do I have here? I've got 4 minus 2, so I've got 2x squared minus 16x, and this is a nice, easy equation to solve. All right, so let's do that here. I'll factor out the 2x, and what am I left with? I'm left with x minus 8. Okay, so it turns out that when x is equal to 0 or x is equal to 8, my derivative is going to be equal to 0. All right, and that means that the slope of the tangent at that point is going to be equal to 0, which is what I'm looking for. Okay, so to fully answer the question now, let me find, we'll do it up here. Let's find y at 0. So that's just, 2 times 0 squared over 0 minus 4. So no issues with a 0 in the denominator. So this is obviously just going to be equal to 0. And let's find y at 8, which is going to be 2 times 8 squared over 8 minus 4. So here, what do we have? We have 2 times 64 over 4. So I'll cancel that out. And 64 over 2 looks like it's going to be 32. So my answers are 0, 0 and 8, 32. All right. So the sort of first thing to do in this question here is to interpret the fact that a horizontal tangent means that the slope of the tangent is 0. Hence, the derivative, which is the thing I can use to calculate slopes of tangents, needs to be equal to 0. From there, use my knowledge of solving rational equations. And then once I've solved for my x values, input to get my y values. Okay, any questions on this one? In particular from whoever asked about it? Okay, no. So if there's no questions, let us move on. So I guess we'll go to page 105. Actually, let's just do 126 because there's only one question there. Hopefully we can get that done quickly. And then there's a bunch of questions on 105. So 126. 2F, I guess it's 127. So 2F. Okay, so we need to find the second derivative there. I think I've got enough space on this sheet. So this is page 127, number 2F, and we want to find the second derivative. So we want to find f double prime at x, and here f at x is equal to, what was it again? It was 2f, right? 2x over x plus 1. All right, so if we want to find the, oh, sorry, got a few people coming in. So if I want to find the second derivative, well, step number 1 is to find the first derivative. So let's do that here. First derivative, gonna have to use the quotient rule. So now I'm gonna start going faster here, okay? Derivative of the numerator, 2 times the denominator function, x plus 1, minus the numerator function, 2x, times the derivative of the denominator function, is just 1. You notice here how I even write it out even if the derivative is 1. It's because remember, this is just that it's an algorithm. So I just want to follow it. I don't want to change the way I do this process, okay, over the denominator squared. Now, because I actually have to work with this function, it makes sense to simplify it before moving on. Okay, so I am going to do the work here of simplifying. So here we have 2x plus 2 minus 2x. And so this actually simplifies pretty nicely, okay, because the 2x is canceled out and I'm actually just left with 2 over x plus 1 squared. All right. So in fact, it looks like my second derivative is going to be easier than my first derivative because I'm just going to rewrite this as 2 times x plus 1 to the negative 2. So I'm not even going to have to use the quotient rule to find the second derivative. So let's do that here. So the second derivative is just the derivative of the first derivative. So 2 is just a constant. I don't have to worry about that. And so now let me find the derivative of this thing here. So again, I ask myself, what's the derivative of u to the negative 2? Well, it's just negative 2 times u to the negative 2 minus 1 is negative 3. Okay. And then I multiply that by the derivative of u, but the derivative of x plus 1 is just 1. Okay. And there's my answer. Now, again, I could leave it like this, but I might as well, you know, get some practices. It's fairly easy to simplify, so I might as well do it. So I notice this whole expression is going to end up in the denominator because of the negative exponent. So what am I left with in the numerator? I'm just left with the negative 4. And in the denominator, I'm going to have x plus 1 to the 3. Okay. And there you go. All right. Any questions on this one here? So again, something to keep in mind that when you do have to find a second derivative or maybe a third derivative, it makes sense to simplify before you move on to doing the next derivative. All right. So if there's no questions, let's move to page 105, which has a bunch of questions there. So 105, we'll start with 9A. Okay, so 9A is actually on 106. So page 106, number 9A. And let's see what they want here. It says state the rate of change of each function at the given value of t. Leave your answers as rational numbers or in terms of roots and the number pi. So I don't think we're gonna have to worry about pi for A. That's probably more for B. So the function here, s of t is equal to t to the 1/3 times 4t minus 5 to the 2/3 at t equals 8. Okay. Now, hopefully you're seeing why they would have chosen a number like 8. Like certainly here, 8 to the 1/3 is a cube root of 8, which is 2. So hopefully some nice stuff happens with these. No guarantee that they're always going to be nice numbers, but let's hope that they might be. So again, obviously the first thing we have to do is find the derivative function. And then from there, we can worry about inputting the t value. Okay, so s prime of t. Okay, so now here, keep in mind, I'm taking the derivative with respect to t. This prime notation assumes that we're taking the derivative with respect to whatever the input is. All right, so let's take our time here since we have some fractions. So derivative of the first is going to be 1/3 t to the negative 2/3, because 1/3 minus 1 is negative 2/3. All right, times the second function, so 4t minus 5 to the 2/3. All right, and then plus the first function, t to the 1/3, times the derivative of the second function. And so now we're going to have to use the chain rule. So if I think of this as u, what's the derivative u to the 2/3? It's 2/3 times u, which is 4t minus 5. Okay, and 2/3 minus 1, I guess, is going to be negative 1/3. All right, and then times the derivative of u, 4t minus 5, is just going to be 4. Okay, so any issues with the derivative? All right, so this is where now we have to make a decision. Okay, do we simplify this, or do we just stick in t equals 8? For something like this, I would say it's a real toss-up. All right, but maybe let's do I would say more times, especially here. What do we have? 4 times 8 is 4 times 8 is 32 minus 5, 26. Okay, it's not the nicest of numbers. I was hoping it was going to be a nicer number there, but we can do it either way. So let's simplify, because remember that question somebody asked about, I think 2b on the sheet that I gave you. You're going to use a similar type of factoring method. Okay, and I think we might have actually seen this in class once. And the idea here is, while it might not really look like there's common factors, there's still some nice factoring you can do. So if I look at my t powers, okay, I have a t to the negative 2/3 and t to the 1/3. And usually what you want to try to do is factor out the exponent that's the smaller one. And the smaller one here is the t to the negative 2/3. Now this is going to work out nicely, okay, because let's kind of look ahead. I'll write it out in a second, but let's look ahead. So I'm going to divide t to the negative 2/3 from this expression. It's just going to come out completely. But what happens when I do t to the 1/3 divided by t to the negative 2/3? Can somebody see what's going to happen? So here I'm dividing two powers with the same base. So I'm subtracting the exponents. And what is 1/3 minus negative 2/3? That's just equal to 1. So you see, by factoring this one out from both expressions, I end up with a much nicer expression there. And similarly here, if I factor out the 4t minus 5 to the negative 1/3, guess what happens when I divide it out from this expression? I'm going to again be left with 1. Okay, so this is where we see where factoring is useful, even though it might not be our sort of usual common factor. And in fact, I'm going to go even further because I notice I'm going to factor out a 1/3 from these two things here. So what I'm going to factor out is a 1/3. I'm going to factor out a t to the negative 2/3 because it's the smaller one. And here I'm going to factor out a 4t minus 5 to the negative 1/3 because it's the smaller of the two. All right. Any questions on what I did here? No? All right. So let's move on. Let's see what we have. The 1/3 gone. The t to the negative 2/3 gone. All right. Now what happens here when I divide this out by 4t minus 5 to the negative 1/3? What is 2/3 minus negative 1/3? It's just 1. So I'm just going to be left with 4t minus 5. Okay, that's all I'm left with here, this nice expression. Let's see what we're left with here. Well, I took out the 1/3, but I still have the 2. Okay. I took out a t to the negative 2/3. So it's what we said before. What is t to the 1/3 divided by t to the negative 2/3? That ends up being just t. Very nice. This got factored out completely. And oh, I also have the 4 here. I guess I should have incorporated that. So times 4. And look how nice and simple this is. Okay. So let's do a cleanup. Number one, this 3 is in the denominator. These things are both going to go into the denominator. Okay. Because they're negative exponents. So I'm not going to worry about what's here yet. I know I'm going to have a 3. I know I'm going to have a t to the 2/3, and I'm going to have a 4t minus 5 to the 1/3 in the denominator. And what are we left with here? We're left with 4 plus 8. So this looks like 12t minus 5. And now I have something much simpler to evaluate. Okay. So S prime at, what was it, 8 is just going to be, and again, I hope everybody was checking my algebra here. So what do we have? We have 12 times 8 is 96 minus 5 is 91. Is that correct? I don't feel like, I want to make sure I didn't make a mistake here. I'm almost certain that's correct, but not taking any chances. So 12 times 8 minus 5.
Tony?
Yeah.
Sorry to interrupt, but I have
Yep.
to go soon.
Yep.
Did you post the answers to the worksheet questions?
I don't think so, but if you're finding derivatives, you can always stick those into the Symbolab derivative calculator.
All right, thank you.
Okay, so I want you folks to start using that. Okay, and then here we've got 3 times. Well, let's see what's happening here. This is 2 over 3. So since I'm inputting 8, I'm going to take the cube root of 8 and then square it, because that's going to be much easier. And then here I'm going to have the cube root of 8 times 4 is 32 minus 5 is 27. Oh, it's 27. Actually, this does work out nicely. Okay, so what do we have in the end? We have 91 over 3 times. So cube root of 8 is 2, squared is 4, and cube root of 27 is 3. And so it looks like we have 91 over 9 times 4 is 36. And I'm pretty sure this does not simplify any further. Okay. So whoever had asked about 2b on the worksheet, you kind of have the trick here. Okay. But can you see that I could have done it from this expression here? It just would have been a little uglier. All right. Any questions on this here? Okay, I'll have to see. I sort of got another request about the sheet. We'll see where we're at because it's already it's 9 now. Okay, so that one was a bit of a long one. Let's take a look at Oh, it looks like 9. I guess, was that the one that was asked? It looks like I've had that one twice. Let's go to number 12 then. Number 12 says, find the equation of the tangent to the curve, blah, 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 at x equals 2. So this is page 106. Page 106, number 12. And again, folks, I do want to encourage you to ask questions as I'm doing this. Okay, so the curve we're looking at here is y equals x cubed minus 7 to the 5. X cubed minus 7 to the 5. And we want to find equation of tangent at x equals 2. Okay. So this is where, as soon as I'm looking for the equation of a tangent, which a line, I have to think I need two things. One of the things I need is going to be a point. So we know that the tangent and the curve share the point at 2. So let me find y at 2 right away. So what do we have? We have 2 cubed minus 7 to the 5. And 2 cubed is 8 minus 7 is 1. So there we go. So our point is 2, 1. Okay. The other thing we need is the slope of that tangent line, and that we're going to get by finding the derivative. And here, I just need to find this derivative. Again, looks like I'm going to be using the chain rule. So take the derivative of u to the 5. That's 5u to the 4 times the derivative of u with respect to x, and that's just 3x squared. Okay. So now that I have my derivative, I can find it at 2. Okay, so I'll clean up a little bit here. So I have 5 times 3, so I've got 15 times x squared, so times 2 squared. And then here we have 2 cubed minus 7, which again is just 1 to the 4. So this whole thing is equal to 1. So we just have 15 times 4, which I guess is 60. All right. And so because I have this great new toy, which is the point slope form of the line, I'm not even going to bother calculating anything. I know I can do y minus the y value, which is 1, is equal to the slope times x minus the x value of the point. And just for good measure, I'll bring that 1 to the other side. Okay. Of course, nothing stops you from taking the slope, the y, and the x value, and putting it into y equals mx plus b, solving for b, perfectly fine. This is just faster. Okay. So in the end, this is especially now that we have these derivative rules, these types of questions are pretty easy because finding the point on the curve, that's easy. Finding the derivative, we have the tools. It's just about inputting your particular x value to find the slope you need. And there you go, you're done, especially if you're using good old point slope form. All right, any questions on this? Nope. Alrighty, let's take a look at, what was the last one? Number 18. 18. So it says, show that the tangent to the curve, blah, 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 at the point 1, 3 is also tangent to the curve at another point. Oh, that's a nice question. That's a very nice question. I think I'm going to have enough room here. So page 106, number 18. Okay. So let's start with my function x squared plus x minus 2. X squared plus x minus 2, all cubed plus 3. Okay. And at the point 1, 3. So what it says is show that the tangent to the curve at 1, 3 is also tangent to the curve at another point. So I guess it makes sense to find the tangent at 1, 3. Let's see what's special about this tangent. And then from there, let's see if it helps us to find some other point with the exact same tangent line. So notice here, it doesn't say just the same slope. It actually says the exact same tangent line. Okay. So I already have the point. I guess I'll find the derivative so I can find the slope of the tangent at that point. And so here, well, the plus 3 is just going to disappear because it's the derivative of a constant. So here I'm going to have to take my good old chain rule. So derivative of u cubed is 3u, which is x squared plus x minus 2. Oops, plus x minus 2 squared. And then times the derivative of u is just going to be 2x plus 1. Okay. So if I now input y prime at 1, what do we have? 3 times 1 squared is 1 plus 1 minus 2. Okay, squared times 2 times 1 plus 1. And here, look what happens here. 1 plus 1 is 2, minus 2 is 0. So the whole thing is 0. Okay. So what is going to be the equation of this tangent line? Well, I know it's a horizontal line. Okay, because the slope is 0 and it passes through 1, 3. So, you know, you might remember this from good old grade 9, 1, 3. If it's a horizontal line that passes through 1, 3, hey, you just look at what the y value is. So that means, oops, the equation of this line is just the line y equals 3. So what we have to do is we have to show that another point on this curve has the equation y equals 3 as its tangent. Okay. But remember, this tangent line has a slope of 0. So why don't we find the other points where the function has a slope of 0? Okay. Obviously, one of them is at 1. Let's find the other points where the derivative is equal to 0. Because we know, obviously, in order to have this tangent, it's also going to have a slope of 0. So let's work with this here. Let's keep factoring. So I got 3. So this is x, I guess, going to be x plus 2x minus 1. Okay. And each one of them is squared because I factor it. It's x plus 2x minus 1. And then I'm squaring each of those. And then times the 2x plus 1. So that means x can be equal to -2. X can be equal to 1. We've kind of already dealt with that, so I don't need to deal with that one again. And here we have x is equal to -1/2. Okay, so the slope of the tangent at each of these points is equal to 0. Can anybody see what we would have to show that it not only has a horizontal tangent line, but that it's exactly the line y equals 3? Anybody have an idea as to what, if I how to check whether each of these has that tangent line?
Well, it goes back into the original formula.
And what am I going to be looking for putting it back into the original formula? What do I need to see when I put this back into the original equation?
That y equals 3.
Exactly, because here at 1, 3, you know, I know the slope of the tangent is 0. So somewhere else, it must also have a tangent which passes through whatever the x value is, and the y value is going to have to be 3. So let's now, by the way, I think you can probably see which one it's going to be. So let's, you know, try, oh, I don't know, let's try x equals -2. And what happens when I put -2 into my function? Well, I end up with -2 squared is 4 plus -2, so -2 minus 2 cubed plus 3. And hey, this whole thing becomes 0. And there you go. So this passes through -2, 3 and has a slope of 0. Hence, the tangent line is again going to be y equals 3. So we've just proven what they asked us to prove, that there was another point that has y equals 3 as a tangent line. Okay. So a question like this, when you look at it, there's nothing particularly special about anything I did. You know, there was no tough algebra. Okay. There's no hard derivatives. It was about, this is really more, this is kind of a really good thinking question, because it forces you to see, it forces you to follow a pattern of thought, to A, say, okay, well, let me find what that tangent line is. And then say, well, if another point has this tangent line, it's going to have the same slope, which we figured out there were two other values that had the same slope. But not only that, it's going to have the same y value. In this case here, -2 had the same y value, hence the same equation. Okay, nice little question. Okay, I'm not sure what that symbol means. I will assume it means that you found this question very exciting. All right. Any other questions? I think I've gone through all the textbook questions now. Anything else from the textbook or any of the ones that we saw? Otherwise, maybe I can take a look at some of the questions on the sheet. Anything else? No? Okay, so let me take a look here at the sheet, what we have. So 2B, again, actually, you'll see is pretty similar to the one I already did. I guess I forgot I had given that other one. So 2B is not really that much of a challenge now that you've seen the one that I've done. I don't know. What were some of the other ones? Somebody said...
Tony, sorry to bother, but if we could just go over 2A, and I guess I'll go over 1B with you tomorrow morning.
Okay, so 2A. It's okay, so let's make this the last one, maybe, unless there's something urgent. Okay, so this is Unit 2, Lesson 2, homework, number 2A.
Yep.
Okay, and 2A, this is very similar to the one we did in class today. So I have f at x equals 2x minus 1 to the 5 over 2x squared minus 5 to the 7. Okay, it's probably like a slightly tougher version of that one there, or pretty similar. Okay, so you should be recognizing this now. You should be recognizing, okay, I'm going to have to use the quotient rule, and I'm going to have a lot of powers. So hopefully I'm going to be able to do a bunch of factoring. Okay, so I'm going to try to do this a little quickly here. So derivative of the numerator is going to be 2x minus 1 to the 4 times the derivative 2x minus 1 is 2. Okay, you see the way now I don't bother with the u and all that. I start to get comfortable just applying the chain rule as is, and then I'm going to multiply that by the denominator function. So minus the numerator function, 2x minus 1 to the 5th, times the derivative of the denominator function, which is going to be 7 times 2x squared minus 5 to the 6, then times the derivative of 2x squared minus 5, which is 4x. All over the square of the denominator. So squaring something to the 7 is just going to make it something to the 14. Okay. And the trick to a question like this is not to panic. Okay, don't panic that it looks terrible, because I'm going to apply that neat little trick to look for as much factoring as I can. So let's look at the numbers. I've got a 5 and a 2 and a 7 and a 4. So there is a common factor of 2. I might as well take it out and make my life a little simpler. Next, I notice the 2x minus 1s, they have 4 of them in common. So 2x minus 1 to the 4. And then I look at the 2x squared minus 5s, and I realize that there's 6 of them in common. So 2x squared minus 5 to the 6. And so now that I take these out, we're going to see that what's left is actually not so bad. So I got rid of the 2. I still have the 5. I got rid of all these 2x minus 1 factors. So the only other thing I'm left with is one factor of 2x squared minus 5. Okay. In fact, this might even be a little easier than the one we did in class. Okay. Minus. So I still have the 7, and I took out a factor of 2. So 7 times 2, which is what's left over. I've got 14. I've got this factor of x. Okay. we got rid of all of these, and I'm only left with one factor of 2x minus 1. Okay. So in the end, this is not going to be quite that bad. Okay. I also notice here, I can factor all of these disappear. I'm going to get rid of 6 of these. So I'm going to be left with an exponent 8. And now it's just cleanup. 2x minus 1 to the 4. Here, what are we left with? Well, I've got 10x squared minus 25, and then 14 times 2, so minus 28x squared plus 14x. And what are we left with in the end? So we're left with 10 minus 28, so that looks like negative 18x squared. And then looks like plus 14x minus 25 all over 2x squared minus 5 to the 8. Okay. And I'll be honest with you, I can't say I'm too motivated to check if this factors nicely or not. By the way, what would be an easy way to check whether this does factor nicely? Anybody remember what a nice way to check that? Think about the quadratic formula. What part of the quadratic formula could I check to see if it's going to have some nice factors? You could check good old b squared minus 4ac. If it's not equal to 0, it means you're going to have a square root in there, meaning not a very nice, not a very nice factorization. But if this b squared minus 4ac is 0, so there's no square root, then it might be worth trying to factor. I suspect it won't. So here b squared, so 14 squared minus 4 times a is negative 18 times negative 25, and that is nowhere near 0. So that means I'm just going to leave this as is. No need to go further. But you see how once I factored these out, look how easy the algebra was. All right. Okay, any other questions, or do we call it a night? Okay, so if there's no other questions, I'm just going to stop the recording, keep it as short as